All right, surface integrals is the next topic. Um, there are two kinds of integrals. An integral over a surface, here's the surface, and we want to parameterize it because that makes the integration more possible, more suitable, easier. Otherwise, this could be a pain. It could be really difficult, especially if this twists around, if this twists or moves or curves in different directions, then this is particularly difficult to do by directly. So instead we use this UV transformation or this R transformation that takes region from the UV plane into this space. If we are integrating as a function of several variables, whose output is a scalar, then what we do is find the cross product of the partial derivatives of this R with respect to U and V respectively, and then we find the magnitude because this is a scalar, and so we want to multiply with another scalar, and then we find the integral over this region as opposed to this surface. This makes things way easier. But again, we have to do the magnitude of the cross product of the partial derivatives of R with respect to U and V. On the other hand, if we have a vector field instead, as opposed to a scalar function of several variables, if we have a vector field, then we still have to do the cross product. However, we don't do the magnitude. That is the difference between that and that. Make sure you understand the difference. We don't do a magnitude. We simply leave it alone, and then we take the dot product of those two. Yeah, so that's the way we figure out each one of those. So those are the two things we're going to cover in this video. Scalar, vector field. Scalar output of a function of several variables, a vector output of, and by vector we mean more than 2 dimensions or 2 dimensions or more, of a vector field, or this would be a function with a vector as an output. There we go. So scalar and vector. And those are the two ways we handle them. Now, if we have a trivial parameterization, that means that instead of using U and V, we're just going to use X and Y. And then we're going to have a function G that represents this, the altitude, the height. So D and S are in the same three-dimensional space, as opposed to D and S being in two different ones. So if this is the case, then if this formula translates into this is a specific case of this formula, this one. So if you actually did the partial derivatives, you will and then the cross product and then the magnitude, you would end up with this output G, derivative of G with respect to X, derivative of G with respect to Y, square each one of them, add them together after squaring, and then add 1, take the square root, and that's that. And for the vector field case, we're going to assume in the vector field case that F of X, Y, Z is made up by 3 parts, P, Q, R. So there's an understanding here. And each one of those would be scalar, a scalar function. And so if you did the cross product, we would end up with exactly this. Opposite of P, opposite of this one, and then the partial of G with respect to X, which G, this G. The partial of Y with respect to Y along with Q, and then plus R, and then we would have the way to find the integral using this. In practice, to be honest, I don't use those formulas. What I personally do is I memorize those two formulas and derive those as needed. But in practice, I only memorize those two. That is the only thing you need, because you can always come up with those if you know the first two. All right, let's do a few a few examples. So start with an example 1. Pretend you have z equals to x squared plus y squared. So that is our paraboloid, and we want to do the double integral of 1 with respect to the surface. So this is the surface. Oh, but actually, it's not going to be all of it. We're going to split this into just a quarter. So we're going to go from here to here. And so this is going to project down on the floor to a circle. Yep. So we're going to integrate over this surface, and the surface will be just this portion of the paraboloid. Yeah, this portion. So only this, a quarter of it, because that is taken over the quarter of a circle. So this would be, there's not much to parameterize. We can use a trivial parameterization. So this would be D, and that is S. So according to, and the scalar function we are integrating is 1. That is a scalar, not a vector field. So according to our formula, this is over S. That would be, let's see, the double integral over D. Yep. And then we would have to do, according to, see, I'm already sort of contradicting myself because I'm ready to use this formula already. Partial of, in this case, it would be Z itself. I guess we don't have to put G, we can just say Z, which is a function of X and Y. So we can do the partial of this with respect to X, and then square that, which would be 2X, square root of 2X quantity squared plus 2Y quantity squared plus 1. And then with respect to the area. Yep. So that would be the double integral of the square root of 4x squared plus 4y squared plus 1 with respect to the area over D. Now, this is a quarter of a circle. This calls for changing things into polar coordinates. Otherwise, we would have to go, okay, so without changing to polar coordinates, we would have to go on the y's. So we're still integrating the same thing for x squared plus 4y squared plus 1 dy dx. That looks like an arctangent of some sort. We will have to make, with respect to y, so 2y would have to be the tangent of theta. Oh, but then we have to multiply by 4x squared plus 1. It gets quite messy if we attempt to do this as is. The limits will go from 0 to the square root of 1 minus x squared because this is the unit circle. But then we will be integrating from 0 to 1, again, because that is just a quarter of the circle. And this can get quite messy to do. I suppose there is a formula, a generic formula we can use from calculus 2, which involves the arctangent. Or instead of doing that, we can just use polar coordinates. So instead, the angle to draw this quarter of a circle is going to be from 0 to pi over 2 on the angle theta, and this is going to go from 0 to 1 on the r's. And then x squared plus y squared is r squared. Okay, so x squared plus y squared is r squared in polar coordinates. So we're just multiplying that by 4. So we have this 4 times r squared plus 1. Dr d theta. Of course, since we're changing to polar coordinates, we have to include the Jacobian. And the Jacobian goes either way. It has to multiply. So we have to multiply by the Jacobian, otherwise we're going to end up with the wrong solution. Okay, this is more manageable. Notice that the expression I'm gonna circle right now, I'm gonna use a different color. This expression does not involve theta whatsoever. There's no theta involved here. So this is a constant for purposes of theta. Remember, a variable, the concept of variable and constant are relative. So for purposes of this integral from here to here, the variable is theta. There is no theta here whatsoever. So all of this is a constant. So we can factor that out. And we just have the integral from 0 to 2 pi of, of 1, I suppose, d theta, which is just going to give us 2 pi. So let's go back to the same. So this is going to be 2 pi. That comes from this integral. And this we're going to do on the side. We can set u, a u substitution, to be 4r squared plus 1. And so du is going to be 8r dr. And we have r and dr, but we have to divide by 8. And then we have the integral of the square root of u du under this substitution. We're not going to go from 0 to 1 because u goes from 1 when r is equal to 0. We go from 1 to, and when r is 1, we go to 5. U is 5. Okay, so we go from 1 to 5, root u du, and then we have to simplify this. That will be pi over 4 times, and then this is u to the 1/2. Antiderivative is u to the 3/2 over 3/2, which is 2/3. And then we have u square root of u, that's u to the 3/2 from 1 to 5. Again, simplify that, and we end up with pi over 6 times, plug in 5 and 1, 5 root 5 minus 1, root 1. So there, this is the exact answer, which, by the way, is I'm just checking something here. This is pi over 2. So this did not match the answer I had initially. 2 pi would be the answer if we were up to 2 pi, from 0 to 2 pi, and that would be for the entire disk. But we are going only from 0 to pi over 2. So there's a mistake here. This should be, I'm going to erase this. I hate to make mistakes in the video. Pi over 2. So multiply those two, and we end up with pi over 16, rather. Yep. Pi over 16. So this would be 16 times, simplify, that gives us 8 times 3, 24. Okay, so let's fix those. That is 16. Yep. And that gives us 24 over here. There we go. Now we're good. Pi over 24 times the quantity of 5 root 5 minus 1. And that is about 1.33. Please, in your solutions for problems I'm assigning, do not box the decimal answer. That is just so that you have an idea of how much it is. By the way, what we just found is the exact area. When we are integrating a surface, we're integrating 1 over a surface, we're really finding the area of the surface. So the area of this surface is about 1.33. It's not 1 and 1/3. It is just a coincidence that we have 1.33. There's other decimals which are not more 3s necessarily. So that is that surface area, about 1.33. If you wanted to find the surface area of the entire paraboloid from up to a height of 1, which is what this is, then we would have to multiply this by 4, and we would end up with pi over 6 times 5 root 5 minus 1. Okay, so this is a first example. Examples are going to get more extensive as we go. They're not going to be short examples. Yeah, because these are difficult problems to start with. So example 2, same surface. Try to draw it a little more gracefully. Same surface. Anyway, but instead of integrating 1, our goal is to integrate z with respect to the surface. So again, this is the surface, and we are integrating z. What does that mean? A point here close to 0, close to the origin, on the surface will have an output value of something close to 0, its own height. So the points here are going to have little value. And as you go higher and higher, we're going to have more and more value to it because they're going to be higher. And if we're integrating z, then that's the value we're using. If we were integrating x, then the points that are on the direction of the x, farther away from the origin, but in the x direction, are going to have more value. So for instance, this point here will have 0 value if we were integrating x. This point, on the other hand, has value 1 because we're integrating z. So depending on what we integrate is how much value we're putting in each one of those points that make up the surface. Yeah. One way to think of it, perhaps, is to think of this function as a density function. So pretend the density here is 0 right at the bottom of the paraboloid. And as we go higher and higher, the density increases up to 1. The most the density will be is 1. So we have a density of 1. And as we go down, the density is lower, down to 0, from 0 to 1. So the density here is a proper proportion of, by that I mean a percentage, a proper percentage of 1, because those numbers are less than 1. All of these heights are less than 1. And of course, we're integrating over this same quarter of a disk as we did in example 1. Now, if we use common sense and think, okay, all of these z's are not going to be more than 1. They're going to be between 0 and 1. That means that we are going to have less, let me write that down. This is going to be less than the double integral of 1 with respect to the same surface, which is, this was from example 1. So I'm not solving it yet. I'm just trying to explain or compare example 1, which is this one, with example 2. And of course, this is going to be greater than 0 because all of the numbers and involved functions are all positive. So we shouldn't have anything less than 0. Okay. So we haven't answered the question. What is this? Okay. And how do we find it? Well, we find it the same way as here, remember? The function in example 1 was 1. Now this function is z instead. All right, so the double integral z ds is going to be the double integral, the integrated integral, z times square root of, remember from example 1, 4x squared plus 4y squared plus 1 dy dx. And y goes in this little quarter of a circle from 0 to the square root of 1 minus x squared, and from 0 to 1. There's more to it. This z, yeah, we are on the surface. On the surface, z is equal to x squared plus y squared. So this is really the integral from 0 to 1, 0 to square root of 1 minus x squared, z, which in turn is x squared plus y squared, square root of 4x squared plus 4y squared plus 1 with respect to y and with respect to x. Boy, this is a doozy, I think. We can change this into polar coordinates. So we're going to change this to polar coordinates. We're going to go from 0 to 2 pi. Here I almost make the same mistake. We're only doing a quarter. I'm so used to doing a whole circle that I almost automatically do the 2 pi. This is pi over 2 because we're going only from 0 to pi over 2, a quarter of a circle. And then on the r's, we're going from 0 to 1. This is r squared. That would be 4r squared plus 1 dr d theta. But let's not forget an extra r, because every time we change from Cartesian coordinates to polar coordinates, we need to include the Jacobian. So that's the price we pay whenever we do this kind of change of variable. Now, as in the previous example, this that I'm circling has no theta whatsoever. So the theta, so we can factor this out from the integral from 0 to pi over 2 d theta, which is going to be just pi over 2. That's one of the mistake I made in the previous example, pi over 2. And now we can integrate this. We can still set u to be 4r squared plus 1. Okay, that is going to cause du to be 8r dr. So we have an r and dr. We have to divide by 8. Okay, and now we got the integral of, okay, the square root of u du, that takes care of the root. This r of the Jacobian is taken care of with dr and the 8 to make the du. But we still have an extra r squared. We did not have this r squared in the previous example, example 1. R squared, if we solve this equation for u, we can subtract 1, so we will have u minus 1, divide by 4, and that gives us r squared. So u minus 1 over 4. U minus 1 over 4 will do it. Okay, and we're going from, not from 0, from 1, because when r is 0, u is 1, and when r is 1, that 1, then u is 5. Oh, wow. So we have 2 times 8, 16 times 4 is 64. Okay, so let's continue down here. Pi over 64. And then we have u, when we can distribute the u with the square root. So we integrate u to the 3/2, because that's a 1.5 of u, minus half of u, minus u to the 1/2 du from 1 to 5. Okay, so we have pi over 64, parenthesis, that's going to be u to the 5/2 over 5/2, so that is 2 over 5, u to the 5/2, which is u squared root u, minus, similarly, 2/3 u root u from 1 to 5. Okay, we can, boy, I don't want to do too many things at once, but we can definitely factor out a 2 from both, and that will reduce the 64 down to 32. Pi over 32 because of that 2. And then when we plug in 5, we're going to get 25 root 5 over 5. Well, 25 root 5 over 5, that's the same thing as 5 root 5. Minus, we're still going to plug in the 5. The 2 is gone because remember we factor out the 2 to reduce the 64 down to 32. So we're going to have 2/3 of 5 root 5. 2/3 of 5. Well, that is 10 root 5, 10 root 5 over 3. But then we got to take away when we plug in the 1, so that is minus a fifth. Oh, again, that's what I get for not doing this step by step. We did say we factor out the 2. So there shouldn't be a 2 there. Yeah, just the 5 root 5. There we go, because the 2 is gone. Now let's plug in the 1. So that is going to be minus 1/5, because the 2 is gone, plus 2/3. Okay, so now it's a matter of simplifying this. Pi over 32. Well, we got 5 square root of 5 minus a third of that. So that is 2/3 left over. So again, this minus a third of itself, that's 2/3 of that thing. So that is 10 root 5 over 3. And then let's do a cross product here. So 3, 10, 10 minus 3 is 7, plus 7 over 15. I'm just double checking my steps real quick. 5 square root of 5 is 5. And then we have 2/3 of 5 root 5. But the 2 is out. Plug in the 1, 1/5, and 1/3. Oh, there's a mistake here. 2/3. I did put the 2/3. Boy, I really have to do this one step at a time. So this is 1. So 1/3 minus 1/5 is 2/15, not 7/15. We can factor the 3. So that will be pi over 96. And then 10 root 5 minus 2/5. That's just the page number. That has nothing to do with the problem. Let me pause for a moment because I want to punch this into the calculator very, very quickly. Okay. Yep, it looks good. There's one thing though. Here, this plus should stay here, plus. And the other thing we can do is there's a couple things to simplify. Let me finish this up in a new page. So we can factor out 2 from those 2, and we should, because that simplifies with the 96. So we really have pi over 48, and then 5 root 5 plus 1 over 5. At that point, might just as well factor out the 5 in the denominator. So that gives us pi over 240, and then 25 root 5 plus 1 will do. So that is, I believe, the most simplified way to write the answer. And by the way, that is about 0.74, which makes sense because the answer, for example, 1 was about 1.33. So we're getting less than what we got in example 1, because in example 1, the function that we are integrating is 1. And here the function is z, but z cannot exceed 1. It's less than 1, between 0 and 1. And consequently, this integral has to be less than that because the function itself is larger. This function is larger than z. If we stay within this radius, if we go outside of the radius, then z will be greater than 1. So that will depend how much we're inside, how much we're outside. There's other factors to take into consideration. But within this radius, the unit circle radius, z is going to be smaller than 1. And consequently, the integral is going to be also smaller than the integral of 1. All right, so that was example 2. Yep. Example 3. Okay. Consider the semisphere, the unit semisphere. So this is just half of a sphere, center at the origin. And we know that z is going to be square root of 1 minus x squared minus y squared. So that is the surface S. And if we wanted to integrate 1, so we want to evaluate the double integral of 1 with respect to the surface. This is 1. So essentially, we want to find the area of the semisphere, which we already know what it is. But we want to use surface integrals to figure this out. And if we integrate 1, that means that we are finding the area. And that means also that each point on the surface has the same value of 1. Nothing is heavier, or we're not giving more value, more weight to any one point over another. All of the points have the same value of 1 as an output. So what is this double integral? Okay, let's just go through this. So this is and by the way, we're using a trivial parametrization. So z equals this as is just the trivial parametrization. And let's recall what we do with a trivial parametrization. Find derivative of that with respect to x, with respect to y, square each one of those, add 1. Okay. So this is the double integral over the unit circle, which is going to be on the bottom of 1. All right. Square root. Well, boy, this is going to get. So the derivative of z with respect to x is going to be negative x over square root of 1 minus x squared minus y squared. And then we're going to square that plus derivative of z with respect to y is going to be similar, negative y over square root of 1 minus x squared minus y squared, close squared, plus 1. And with respect to the area, not over the surface anymore, but the circle that is at the bottom, the projection of the surface over the floor, which is going to be the unit circle, that's what we're going to integrate over. So this is the unit circle. Okay, let's simplify this a little bit, clear this up. So I don't want to put down a limits of integration yet. I just want to leave it as d, because I don't know how this is going to turn out yet. But let's do it. So this is going to be the square root of, when we square the first term, we're going to end up with x squared over 1 minus x squared minus y squared plus y squared over 1 minus x squared minus y squared plus 1. But 1 can be written as, so we have the same common denominator, 1 minus x squared minus y squared in the denominator, and the same thing on top, and that causes us to have 1. Okay, since we have the same common denominator, x squared and x squared add up to 0, this negative and that one being positive, that also is 0 over the same domain. And that is going to be the double integral of, so we end up with 1 on the numerator, square root of 1 is 1, over square root of 1 minus x squared minus y squared. Yep. All right. If we were not going to use polar coordinates, this would be dy dx. Y would go from negative square root of 1 minus x squared to the positive of that, because we have a unit circle, and from negative 1 to 1, which is messy. It's long. I don't want to do that. So instead, we're going to change to polar, and we're going to go from 0 to 2 pi, because we do have the full circle this time. And from 0 to 1, because we have a unit circle, and we're going to have on the denominator square root of 1 minus r squared, because x squared plus y squared equals r squared, dr d theta, and of course we may not forget the Jacobian. Yep. So because we're changing into polar coordinates, this integral has nothing to do with theta, so I might just as well factor it out. So we end up with the integral of 2 from 0 to 2 pi d theta, which is going to give us 2 pi. For that integral itself, we're going to change the variable. We're going to use u to be 1 minus r squared. And so du is going to be negative 2r dr. We have the r and the dr, but not the negative 2, so we have to multiply by negative 2, well, negative 1 over 2. And we're going to have the square root of u in the bottom. So because I want to use the power rule, I'm going to say u to the negative 1/2 du. And when r is 0, we are at 1 and 0. So those two flip because of the way this is constructed. So the 2 and the 2 cancel. We end up with negative pi. The negative doesn't cancel, at least not yet. And then we have u to the 1/2 over 1/2, so times 2. And then u to the 1/2 from 1 to 0. I'm going to try to squeeze that down here. Negative pi times 0 minus 1. So that gives us, oh, I'm missing the 2. There's an extra 2 there. Let's just squeeze it here, 2 times negative pi. So we have 2 pi, which we already knew. The area of the unit semicircle is 2 pi. The area of a full, I didn't mean circle, I meant sphere. The semisphere is 2 pi. A full semisphere, unit semisphere, the area of the surface would be 4 pi. So yes, this, and if we didn't know that, now we know that. Now we know what it is and how to obtain that. Of course, we could have done that also in Calc 2 by finding the surface area, because this would be a surface area where the surface is produced by revolution. So we could do that also. However, it is good to do this from the multivariable point of view. Example 4. Okay, so same as example 3, but the function will be 1. Okay, so we still have the same semisphere. I didn't mean that, I meant z. Otherwise, we have exactly the same example, z. The same surface, But now we're going to put value other than 1. So when this was equal to 1, every one of those points will have the same weight, 1, 1, 1, 1, 1, 1, 1, the same output. But here, their weight, their output will depend on whether they're located. If they're closer to the XY plane, then their output is going to be 0. So down here, 0, 0, 0, 0, 0, 0, 0, 0. On the top, 1. In between, well, numbers in between 0 and 1, proportionally depending on the height, not depending on where they are on the actual curve, but depending on the height. Yes. So there's going to be, numbers clustered around. The top are going to be quite heavy, and the numbers here on the band towards the bottom are going to be close to 0. Now, all of this, within this sphere, all of these guys are going to be less than or equal to 1. And so the answer we obtain better be less than 2 pi, which is the answer we obtain in example 3. Just as example 1 and 2, one was smaller than the other. Similarly here, one is smaller than the other because the z's are going to be less than 1 themselves. Okay, so the double integral of z, and this is the surface S. And by the way, the bottom, just the bottom, is what we call D. Yeah, so z, with respect to the surface, the double integral, okay, is gonna be the double integral of z. By the way, z in this case on the surface is x, whoa, I almost put x squared plus y squared. It is the square root the z is the square root of 1 minus x squared minus y squared. There we go. So that's what we're going to integrate, square root of 1 minus x squared minus y squared over d. We're using what parameterization? Trivial parameterization. So now we would have to do the square root of partial of this with respect to x, quantity squared, partial of this with respect to y, quantity squared. Add 1 to that, and simplify it. But we did this in example 3. Yeah. Technically speaking, we would have to do all of this after 1. In this example, we would have to do all of that after this z. So z is 1 versus z is that, and we still have to do this big, gigantic root. Well, let's follow the steps. This gigantic root became this, which simplified down to that. So instead of doing the whole thing, let's just stick with this. We already did the work in example 3. So we have 1 over that root. 1 over square root of 1 minus x squared minus y squared with respect to the area. And this factor came as part of example 3, which we just did because that is example 4. Well, that is neat because that means we are double integrating just the number 1, because those two simplify, with respect to the area over d. That is this area. This is a unit circle. I might just as well use geometry. So the answer is pi. Yes, so the double integral of z with respect to the surface of this surface, that is the semisphere, is pi, which is smaller than 2 pi, which is the answer we obtain in example 3. And the reason is because the weight is always less, except for the very top where it will be equal to 1. Otherwise, we're going to get less than 1, as opposed to the previous example where the weight was 1. And by weight, I mean how much there is in the output of the function. Yeah. So this is a neat example. Example 5 is not going to be as simple. All right. So example 5. Oftentimes, we have to do an integral of a surface, but the surface is the shell or the skin or the outer layer of a solid. So sometimes the surface is the boundary of a solid. So many times, actually, many times, as we will see soon, the surface will be the entire boundary of a solid. So pretend you got a unit cube. So each side is 1, and the height is 1. And this cube is located such that the back lower corner is on the origin. So this cube goes from 0 to 1. So this point here would be 1, 1, 0. And then 1 unit above. I don't want to put coordinates everywhere because then the picture doesn't look as nice. But that would be 1, 1, 1. This is a 1, no, it's 0, 1, 1. And this back point, let's put this one here, is going to be 0, 0, 1. And we have a perfect cube. So so the surface is all of that, all of it, the 6 faces. So in this example, the surface S is made up by all 6 sides of the cube, of the unit cube wall. So we're going to have a bottom, a top, right side, left side, as we are facing this, front, and back. So there's going to be 6 sides. Now, we're going to use different equations for each one of the sides. So for instance, on the bottom, what do we know about the z on the bottom? The z is equal to 0. And we can integrate x and y, or with respect to x and y, as x goes from 0 to 1 and y goes from 0 to 1. So x goes from 0 to 1, and so does y. Okay, so that's just the bottom. The top, z is equal to 1. And x goes from 0 to 1. And so does y. Okay, so that's 2 out of 6 faces. We got to do this for every face. All right. On this side, on the front and the back and the sides, z varies. We have to see, this is one of those cases that where we have to parameterize the walls, the sides of this cube. Anyway, what is our goal? What is the question? Okay, so evaluate the integral, the double integral over the surface. What is S? All of that, all of these 6 sides of Z with respect to the surface. So this is the question. We want to evaluate that guy. In order to evaluate that, we have to evaluate this integral over the bottom, over the top, and each one of the other 4 faces. So let's do that one by one. Let's call the bottom S1. So S1, that's an S. That's why my S is sometimes S1. There we go, that's better. S2 is gonna be the top. And then we're gonna label the other ones as we go. Okay, so put a period. So we have a new integral. Okay, so bottom, yep. We're gonna double integrate as y goes from 0 to 1, and so x goes from 0 to 1 as well, z. But what is z at the bottom? Well, z is 0. So we're going to integrate a big 0. That's what z is at the bottom, z at bottom face. So the answer, of course, is going to be 0. Okay, that wasn't too bad. We have to do 6 of those. 1 down, 5 to go. Okay, at the top, okay, we're going to double integrate from 0 to 1, from 0 to 1 on the y's and on the axis. All right, but we're going to integrate 1. Okay, that's the value of z at top face. And so, of course, we're just going to get the area of a regular square. So the answer is 1. Okay, we got 2 down, 4 to go. All right, now we got to parameterize the, let's start with the back side. Back side. So on that side, x is equal to 0. And you may be thinking, well, so that means the x, no, not that easy. The x is 0, so then we're going to end up with 0. I don't know. No, I think it's best to parameterize because this is, remember, when surfaces go around, then the integrals are tricky. Then it's just best to parameterize. So x is 0. And we can simply parameterize. So let me make a square here because that's not part of this. What we're doing here is not part of this. So this is the back side. Okay, x is equal to 0. And so perhaps we want to change it. So there's no x is 0. But then the y varies. So on the back side, y varies across between 0 and 1. And so does z. So we can go from we can call this u and v. So what this parameterization does is we take a square from the UV, pretend that it's a square, from the UV plane, and we place it here. This is the back side of the cube. So R does that. We take a square on the plane, on the UV plane, and we place it on the X, Y, Z. Okay. So the back side, let's do this on a new page because I don't want to, this is going to be more involved. 5. So this is 6. I'm putting my pages. And 7. Okay. So we're still developing the back side. Double integral. Okay. So R UV is equal to 0 UV, and U will go from 0 to 1, and so does V. Oops. Okay, so we want the double integral of Z, let's put it in general, and let's label this as S3, the backside. S3 with respect to the surface. Okay. I'm thinking because our formula we had on our very first page at the beginning, when we have a general parameterization, we have to find R sub U, R sub V, cross them, and then do the magnitude in order to come up with this, which I still work we have to do. Yeah, this is not a trivial parameterization. We use this formula as we did in previous examples if we had a trivial parameterization, if we're using X, Y. But here, we're using U and V, which don't fall into the same spots as X and Y fall. So we have to figure this out from scratch. Okay. R sub U would be, as you would know, 0, 1, 0, because that's the only one where there's a U. R sub V would be likewise 0, 0, 1. By the way, this is J, this is K, the vector J and K. I don't personally, that's my personal, very, 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 very personal. I prefer to use coordinates over names, but that doesn't mean that is wrong. Using names is wrong. It's just a preference. So you do know though, J crossed with K gives us I think. 1, 0. Yeah, it does give us I. All right. If it's clear enough, sometimes I omit the commas. If only if it's clear enough. But then we want the magnitude of that. And of course, the magnitude of a three-dimensional vector where two coordinates are 0 is just the absolute value of the coordinate that is not 0. Boy, that was a mouthful. Anyway, it's clear that the magnitude of this is 1. So this is equal to double of Z. In this case, Z is V mind. And then 1, V is not a vector, it's just the variable V. This 1 comes from R sub U cross R sub V, the magnitude of that, du, dV from 0 to 1, from 0 to 1. And that's going to give us, well, uv, so the integral, uv, but from 0 to 1 is just v dv, again from 0 to 1, and that's going to give us v squared over 2 from 0 to 1, which is going to be half. Whoa. So the top is 1, the bottom is 0, the back is a half, the front, okay, front side, we're going to use a different parameterization, RUV. So let me put a line to, I got so excited that I circled that, and I did not circle the other two. We got 0, 1, and now a half. That was the back. The front side, well, on the front side, let's see. There's the box. Yep, on the front, so this is the front. Let's see. X is 1, and then we can parameterize Y and Z with U and V. See, we don't have a trivial parameterization. No, we do have a trivial parameterization if U, V were here, U and V in that order. As soon as we don't have that, we don't have a trivial parameterization, which means we gotta go through this exercise of derivative with respect to U, which would be 0, 1, 0, derivative with respect to V, which is still 0, 0, 1, cross product R sub U cross R sub V is gonna be 1, 0, 0, and the magnitude R sub U cross R sub V is gonna be 1. 1 squared plus 0 squared plus 0 squared is 1, and then we take the square root of that, so that's 1. And then still Z is gonna be V, and remember, we're integrating Z. Let's label this as, actually not, f. I put f for front, but let's call it s sub 4. So the double integral over s sub 4 of z, or v, I guess it depends how far back you want to start with. So that is the iterated integral of v times 1, and 1 comes from the magnitude of the cross product of the partials of r. dy, whoa, the whole point of this is not to use y. Yeah. Du dv, or dv du, I suppose. dv from 0 to 1, 0 to 1. Well, we did that work back here, so there's no need to redo it again. So we end up with 1/2. So far we got, what did we start with? There's 6 faces to do. 0, 1. 0 was the bottom, yep. 0 the bottom. 1 is the top. 1/2 is the back. 1/2 is the front. How about, let's do a new page. 8. How about the right? No, the left side. Left side. So we want to parameterize this side. Again, that's the left side of the cube as we face it. So it's not its left side, it is the left side as we perceive it. And let's label that as S5. Well, the parameterization will have to be, okay, so RUV, let's see, Y would have to be 0 at all times, so we can just do U0V. Okay, this is different. R sub U would be 1, 0, 0. R sub V would be 0, 0, 1. Yep. The cross product would be 0, 1, negative, and then 0, which makes sense. This is I multiplied with K, cross product with K. Anyway, so this is negative J, but we don't care whether that's negative or positive because we want the magnitude. And that's going to be 1. V is Z. So S5 ZDS is the iterated integral of V UV. Oh, there's a 1 that I'm missing. I better not forget it. Times 1, and that 1 comes from that. So pay close attention to that because sometimes that won't be 1. It will be something different. 0, 1, 0, 1. We've done through this exercise a couple of times. The answer is 1/2. And then we have the right wall, the right side, the right side, I guess. So we got to parameterize the right side, which is going to be here, which is going to have the same, well, let's write down the parameterization. RUV is going to be X can extend out this way, U. Y is stuck at 1, and V is going to be the Z, and it changes. So after this, everything else will be the same. We have V as Z. The derivatives are going to be the same. So the double integral S6 Z ds will be, again, 1/2. Okay. So finally, the conclusion is that the double integral of Z with respect to the surface over the entire cube, and by that we don't mean the cube inside, but the shell, the surface of the cube, will be 0 for the bottom, 1 for the top, and 1/2 for each one of the other faces, which makes sense because we're evaluating z, which puts more value on the top. It puts a value of 1. Here, the value varies from 0 to 1, so it kind of makes sense that, and because this is so uniform, we're going to get 1/2. Whoops, I don't know what that is, but let's put it what it should be. A 2. So back side, front side, left side, right side, 1, 2, 3. So the final answer is 3. 1, 2, 3. Interesting. So that is the double integral of the entire surface around the cube of z. As you can tell, these examples are not trivial. Okay, new example. Boy, and they're getting harder as we go along. So the next example is example, boy, I already lost it. That's example 6. This is going to be much more complicated, I think. And I don't want to lose my page numbering. So this is going to be my page 9, my page 9. Okay. Okay, so we're going to have this shape, which is part of a plane. The plane will be z equals y plus 2. So there's a plane that contains this, which is not a circle because this is the intersection of the cylinder with the plane. So this is a plane that is oblique. And then we're going to have a circle down here. That is going to be the unit circle. So the bottom is going to be x squared plus y squared equals 1, the unit circle. That's the plane on the top. And by the way, at the bottom, z is equal to 0. So that's a plane on the bottom, a cylinder, and a plane on the top. And we end up with a solid. This is the solid. So it's a truncated cylinder. On the bottom, it is flat, horizontal. On the top, it is not horizontal. It is cut at a 45-degree angle because here we have a slope of 1, and a slope of 1 is the same thing as tangent of 1, which is the same thing as tangent of 45 degrees. Or a tangent of an angle equal to 1, which is pi over 4. The angle would be pi over 4, and that is 45 degrees. Okay. So this point here is 0, 0, 2. 0, 0, 2. And because we got a 45-degree angle, this goes up to 2. No, 3. So that would be, okay, so let's put some coordinates. This goes down to the origin. The origin is down here. Yeah, the x-axis is that way. And then we got the y-axis here. But the y-axis also extends to the left here. So this point is 0, negative 1, 1. This point is 0, positive 1, 3. This highest point, the lowest point. And then we can figure out the point on the sides, which are going to be 2 on the axis, 2 and negative 2 on the axis. No, I lied about that. Because we have to go up from the unit circle. So we got to go 1 and negative 1 on the x-axis. And then the y is going to be 0 because, yeah, we're looking at this point that is across on top of the x-axis, so y is going to be 0. And then to figure out the height, that is going to be 2 as well. Yeah. Anyway, so the question is, we're going to make 2 problems out of this. Yeah. First, we want to integrate, double integrate. So the surface is all of this over S1 ds. So let me establish that S at the bottom, this S equals the surface, which is the entire boundary of the solid. So there's going to be 3 parts to it. The bottom, there's going to be a top, and then there's going to be a side. So the side is all the way around. 1 bottom, 1 top, and 1 side, as opposed to the cube that had 4 sides, the front, the back, you know, left and right. But here it is just 1 smooth side. Okay, the bottom is going to be represented with S. So let me draw a new picture here. So this is going to be S1, this is going to be S2, and then the side, S3, is going to be around. So there's going to be 3 sides. So this integral is going to be broken up into the integral of S1 or over S1, over S2, and over S3. And as in example 5, we're going to add all of those to obtain the final integral of all of that surface. So let's talk about the bottom. Well, the bottom is not too bad because we're going to integrate 1 over the bottom. Well, that's just the area of the bottom, and this is the unit circle. So the bottom, on the bottom, so let's call it S1, 1 ds, is just going to be pi. It's just the area of the bottom. If we're integrating 1, if we're doing a double integral over a surface, and what we are integrating is the number 1, we're just getting the area. Whoa, there's a lot of ink on my hand because of this pen. So the same thing will happen on the top. Top, double integral, S2, 1 ds. If we know the area, then might just as well write it down. Now, anytime we are intersecting a round circular cylinder with a plane, you're going to get an ellipse. This is not a circle on the top, it is an ellipse. Let's talk about that ellipse for a moment. So let me draw it fairly large. So this point is 2. Actually, this point is 0, 0, 2. This point, we did say it is 0, 1, 3. So to go from this point to this point, we're going 1 unit because we start at 0, but then we go from 0 to 1 on the y. So to the right, 1 unit. And then from 2 to 3, we go 1 unit as well. So this distance, because this is a 1-on-1 right triangle, would be the square root of 2, this distance. The distance across, picture is going to be kind of weird, but there's the distance across. So this is parallel to the x-axis, will be 1. This point here would be 1, 0, 2. So the only thing that is changing compared to 0, 0, 2 versus 1, 0, 2 is just a 1. So this distance is 1. So this is an ellipse, like so. This side is square root of 2. This is 1. I'm not putting the x on the y-axis correctly, and I just want to know what this is and that is, because we have seen in a previous video what the area of a generic ellipse is. If this is A and this is B, the area would be pi AB. So in this case, we have pi, so the area of this ellipse is pi times 1 times the square root of 2. So pi square root of 2. So we could do the whole integral and everything, but, and you're welcome to do it, square root of 2, and then pi outside of the root. I should have put pi square root of 2, but all right. So the bottom is pi, the top is pi times square root of 2. Now the sides. And the reason why I wanted to do this fast is because the side is more complicated, as you probably. Okay, so let's see. So we want to parameterize S3, which is the side. How do we parameterize that? Well, first, we need to parameterize the circle. The circle, but we know how to do that quite well. The bottom circle can be parameterized with, okay, so R, U, V. Okay, so the bottom can be thought of as, let's put 0 for now. Is going to be cosine U, sine U. Okay, and that creates this circumference, comma, 0. And now we're going to create a height. So R, U, V will be cosine U, sine U, and let's make the height just plain V. The trick here is that V is going to be bounded by 0 and this top. Now remember, that top was Z equal to just the top, Y plus 2. So this V is going to be bounded on the bottom by 0, but on the top by, watch, Y plus 2, or 2 plus Y. This is Y, this is X, this is Y, and this is Z. X, Y, Z. So Z, which is how much we're going to go up, is bounded because it varies. Here it's going to be up to 2, from 0 to 2. On this end, it's going to go from 0 to 3. On the back, it's going to go again from 0 to 2. Over here, from 0 to 1. So how much are we going to be bound in the height depends on where we are in the circle or on the circle. So 2 plus sine of U, while U goes from 0 to 2 pi, all around the circle. So we start with 0, add 1, eventually when we get to 90 degrees, 0 again. So from 2 to 3, that's the 1, back to 2, down to 1. So sine will do this perfectly. Okay, now you gotta really visualize this well as we do this problem. So we wanna double integrate over S3, 1 ds with respect to the surface. Okay, so the question is, oh, there's more to do. So this is our parameterization. I'm gonna box it. And remember, we have to do R sub U. So that is negative sine of U, rather. Negative sine of U, cosine of U, 0, R sub V, 0, 0, 1. r sub u crossed r sub v, cosine of u, and 0. Sine of u, positive, and 0. Magnitude of r sub u cross r sub v is going to be cosine squared plus sine squared, which is 1, plus 0 squared, still 1, square root of that, 1. So that came from that. Again, cosine squared plus sine squared, 1, plus 0 squared, still 1, square root of that is 1. Okay, always check that because oftentimes the magnitude of the cross product is not 1. Okay, so we're going to integrate from 0 to 2 pi on the u's, and on the v's from 0 to 2 plus sine of u, from 0 to 2 plus sine of u. 1, that the first one is, that's the output of the function. 1. That's the output of the function. The second one I'm going to put, which is going to be still equal to 1, that's a 1, comes from this. Yep. Yep. Yeah. By the way, what we are doing is we're taking, this is not a plane, so u goes from 0 to 2 pi, 0 to 2 pi, and then v is 2, 1, 2. We're taking this surface and we are making the surface that we need. Whoops, that's much more tilted. We're getting this surface. We're changing this into that by wrapping it around the unit circle. That's what we're doing. Isn't that neat? We're taking, so if you actually, and this is quite geometric, if you cut here and open this out and you spread it, you're going to end up with this surface. That's kind of neat. dv du. Okay. So that is the integral from 0 to 2 pi. 1 is easy to integrate. We just end up with, and starting with 0 makes it even easier, 2 plus sine of u du. We're integrating sine of u from 0 to 2 pi, so that's going to be 0 when we integrate. So we end up with just 2 from 0 to 2 pi, which is 4 pi. By the way, we're finding the area. When we integrate 1, we're finding the area. So the area of this guy is 4 pi, which makes sense because this height is 2. 1, 1, 2, 3. 1, 2, 3, and this is 2. If you cut across perfectly, well, my sine function apparently is not perfect, but this extra excess over this line matches perfectly with the deficit with respect to this line. So those two undo each other. So this is a rectangle of area 2 pi by 2, 4 pi. Okay, so the total integral of 1 with respect to the surface of the entire surface S, which is all the 3 faces, will be bottom, I'm going to continue down here, bottom, which is pi, top, which is pi square root of 2, sides, the side, which is just one side, 4 pi. So we end up with pi, 5 plus 1 plus 4 is 5, square root of 2. And there is our final answer. I think that is neat. As you can tell, those problems are very, 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 very involved. Okay. I'm just looking at example, next example. Example 7. My page 11. Okay, so guess what it's going to be? Same as example 6, but function that we're going to integrate is z. So we integrated 1 in example 6. Now we're going to integrate z. Okay, so same shape, same thing as example 6. The bottom will be, so let's label the bottom as S sub 1, top S sub 2, the side S sub 3. Is that how I labeled the previous one? Yeah, I did. Okay, so the double integral of z on the bottom, oops, not z, s. Okay, on the bottom, well, remember that's on the bottom, on the floor, xy, on the xy plane. And the xy plane, all the z's are 0. So this is going to be 0. So the whole thing is going to be 0 on the floor. On the floor, by the way, when we were integrating the previous example, we obtained pi. Now we got 0 because the z value on the floor is 0. Okay, so that's done, checked. We got 1, down 2 to go because there's 3 surfaces to integrate over. Okay, so the second integral, S2 z ds. Okay, so now remember the surface here, or the plane going this way is y equals 2 plus y. I didn't mean y, z equals 2 plus y. Z equals 2 plus y. Okay, so a generic point here on the, well, first let's start on the bottom. A generic point here will be an xy point, and the height will be, so a trivial parameterization, that's what I'm trying to say. A trivial parameterization would be, okay, so let's talk about the top. Okay, so we can have r of xy equals xy, and then z would be 2 plus y, 2 plus y, over the unit circle on the bottom. If we did that, then we have to do, okay, so this, I'm going to continue down here, equals integral. Now we're integrating over x and y in the unit circle up here. So on the unit circle, we're going to go from -1 to 1, 1 minus x squared, negative, 1 minus x squared positive on the top. Z is 2 plus y, quantity 2 plus y. And then we have to remember, if we are integrating, we have to do this business. Z with respect to x squared, z with respect to y squared plus 1. So far we just wrote down this portion, but then we have to figure this out. So this is z with respect to x, z, this is z with respect to x. Let's write that down here. So, okay, so z equals 2 plus y. Z sub x is 0. Z sub y is 1. Okay, so that's easy. Z sub x, 0 squared, 1 squared. And then there's another 1 showing up, 1 squared. dy dx. Okay. So that is just the square root of 2. The square root of 2 may factor out. Okay. And then we're integrating 2 plus y. Y, with respect to y, is an odd function. If you're integrating from negative of a number to positive of the same number, an odd function, that's going to give us 0. And you can just do it yourself. So this is going to vanish. The y portion is going to vanish because that is an odd function relative to y. The 2, well, the 2 is easy. The 2 is just a constant. So you just do the top minus the bottom, which is double the top. So we have the 2 from the integration. And the top minus the bottom is going to be another 2 of the square root of 1 minus x squared dx from 0, from negative 1 to 1. Now let's just make sure. This 2 is this one. Well, first of all, 1 plus 1, square root of that, that's the square root. This 2 came from that. The second 2 came from doing the top minus the bottom, because we're just integrating a constant. So this minus negative that of the same thing is just 2 of that, the first one. So that's the 2. This is a semicircle that we're integrating from negative 1 to 1, the unit semicircle. So that is going to be pi over 2. So we're going to have square root of 2 times 2 times 2 times pi over 2. 2 of those cancel. So we end up with 2 pi square root of 2. 2 pi square root of 2. 0. Now we got 2 pi square root of 2. Okay, so I'm going to, let's do the next one here. I was going to start writing the conclusion, but I better wait before we start writing the conclusion. Okay. Now, I'm going to piggyback on the previous example for the parameterization of the side. So now we got the side wall. All right, the parameterization we used, UV, was cosine U, sine U, and then 2 plus y, so 2 plus sine, no, scratch that. Except that we're not going to scratch it, we're going to erase it. So what is the V? There we go, V. And the V is bounded by 0 and 2 plus y, 2 plus sine of u. And u is going from 0 to 2 pi. Okay. So we're going to do the double integral over the side wall. I could have called it just S3. But we are integrating z. Yep, z over the surface. Z is V in this case. V. And then example 6, we did have this. And remember, we did all of this work to figure out the cross product of R sub U cross R sub V. So let me make a note here. R sub U cross R sub V was equal to 1. So we multiply by 1. dV du, as V goes from 0 to 2 plus sine of U, and U goes from 0 to 2 pi. There's a lot of information here. This is not trivial by any means. So we're going to have V squared over 2. But we're going to plug in 2 plus sine of U. Yep. So from 0 to 2 pi, 2 plus sine U, quantity squared over 2. du. V squared over 2, plug in that, plug in 0, yep. All right, let's put the 2 out, the denominator rather. And so we're going to integrate from 0 to 2 pi, 4 plus 4 times sine of u plus sine squared of u du. Okay. 4 is just going to give us 4 times 2 pi. So that is, let's write it down, 4 times 2 pi. That's easy. Plus a full period of sine. Well, that's going to be 0. Well, 4 times 0. Plus sine squared. We have done this several times, several times. So let's cut the time. And by hand, by the way, we haven't used a calculator to do this. But we have done it several times. Remember, this is 1 minus cosine of 2 theta over 2. And then we go from, so the cosine of 2 theta, the integral of the cosine of 2 theta is equal to 0. So that goes away. So we end up with a half, but then we're going from 0 to 2 pi. So the half cancels with the 2 pi. And we end up with just pi. Yep. All right. So that vanishes and we end up with 8 pi's and 1 pi is 9 pi's over 2. Thus, the double integral over the entire surface of the solid of z ds is the bottom, the top. Now I forgot what the top was. That was like stuff. That's a different example. 6, 7, there it is. The top is 2 pi root 2 or 2 root 2 pi plus 9 pi over 2 for the side. So we end up, we can factor out the pi. In fact, I'm going to factor out pi over 2, and we end up with 9 plus 4 root 2. 4 root 2 plus 9. Yep. And that should be our final answer for the entire solid. Okay. These examples are not easy. Okay. The flux is the double integral over of a vector field over a surface. So it is pretty much what is retained or goes through a membrane, this surface, which is a membrane, and how much of the fluid is crossing the membrane per unit of time. So that's kind of what we are measuring. It's a good idea to start with something easy and simple. So example 8. Example 8. Okay, so the surface is just going to be a unit square that is lifted up 1 unit. So this coordinate is 0, 0, 1. This coordinate is going to be 1, 0, 1. This coordinate is 0, 1, 1. This coordinate is 1, 1, 1. So that is the surface. That's it. That's S, no more, not 6 sides of a cube, nothing like that. It's just a surface. That's it, just one surface. And F of X, Y, Z is going to be 0, 0, 1. So we're going to have all the vectors going up. All the flow is going to go up in the same direction, all the way up, and in the same amount. So the question is, what is the double integral of this over that surface? The parameterization of this surface is fairly trivial. R of xy is going to be xy, and then just 1 for z, and x and y are going to go from 0 to 1. R sub x is going to be 1, 0, 0. R sub y is 0, 1, 0. The product, as you guys know, will be, so this is ij, the cross product is going to be k, 0, 0, 1. So we're going to have 0, 0, 1 for the field dotted with 0, 0, 1. Now here, we're not going to do the magnitude as we did in the previous examples. We're just going to have the vector 0, 0, 1 over y and over x as we go from 0 to 1, because those are the boundaries of this parameterization. Of course, that's going to give us 1, and then we're just going to integrate relative to that. So integrating 1 over this square is just going to give us the area anyhow, or you can just do it. And the answer is going to be 1, which makes sense. All of it is going to go through. Example 9. Pretend the vector field will be, we want to go up in this to the right. So 0, 1 over the square root of 2, 1 over the square root of 2. The reason why we don't have 1, 1 is because we want to be, compared to this example, the magnitude of the vectors is 1 unit. And the magnitude, we want to preserve that magnitude. We don't want to change, we want to change the direction without changing the magnitude. So the magnitude of this will be 1. It is, this vector field will be a vector, all the vectors are going in this direction, up to the right of us at a 45-degree angle. And all of the vectors are going to be in the same direction. So the question is, okay, how much of that is going to go through this membrane, the same membrane we're using there, or the same surface, S? Well, let's see what changes. We already figured out this membrane's parametric representation, which would be, or the vector we're using for that is the cross product, which is 0, 0, 1, the cross product of the partial derivatives. What changes is that this vector will be, instead of 0, 0, 1, it will be 0, 1 over the square root of 2, 1 over the square root of 2. So the double integral, the flux, that is also called the flux, S, F, with respect to the surface, will be double integral from 0 to 1 on the x and the y's. And we're going to dot 0, 1 over the square root of 2, 1 over the square root of 2, dotted with 0, 0, 1, dy dx from 0 to 1, 0 to 1. So notice that this is going to drop. And the only thing that is going to survive after the dot product is one of the two components, 1 over the square root of 2, just because of the way this cross product came out to be. So we will end up with 1 over the square root of 2 instead. Because we're integrating, after factoring 1 over the square root of 2, we're just integrating 1 from 0 to 1 and 0 to 1, just 1. And that's going to give us 1 over the square root of 2, which is less than what we obtained back here, 1. So the answer is 1 over the square root of 2. Just like up here, the answer is 1. Yeah. So going this direction is going to be less efficient as far as catching the flow. We're only going to be catching 1 over the square root of 2 as opposed to a whole 1. 1 over the square root of 2. Let me use my calculator real quick. 1 over 2 root equals, so about 70% or 71%. This is about 71% of what we would have been able to catch if this surface was tilted. So if this surface was 90 degrees with respect to the flow, we would catch everything. 1. Everything is 1, 100%. 1 is 100%. Instead, we're catching 71% of it because of the angle. I'm going to let you do example 10. Example 10. Assume that same surface, but assume that F is going totally horizontal to the right. So 0, 1, 0. And find the double integral over the same surfaces as example 8 and 9. Yep, of this particular F with respect to the surface. Yep, and you can probably guess what it will be if the vectors were going horizontal and we were trying to go through the same membrane. By the way, the reason why, because this could be anti-intuitive, because the area did not change. So how come we're catching less? One way to think of it is the shadow. You know, if your shadow is, if the source of light is on top of something, then the shadow will be the same size of the object that's producing the shadow. But if we are at an angle, then the shadow will be longer. It's the same kind of situation. So the shadow of this pen, oh, I have to turn some lights off. I have too many lights going on here. But the shadow of a pen under one of the lights is pretty long. Let's see. Yeah, it's, whoa, it goes way out here. So it's much, much longer than if we just had a light on top. I could play with the lights, but let's move on. So that was example 8, 9, and 10. Okay, let's do an example 11. And I just want to keep track of my pages. That was page 13. This new one is page 14. On my notes. Okay, so the membrane or the surface is going to be a semicircle, unit semicircle. So remember, same kind of semicircle we've been doing or working on before. And now the vector field is going to be 0, 0, 1. So if we go perfectly up 1 unit, how much of it is going to go through this? Now, some of it is not going to go very efficiently on this side because this is more vertical. Over here, a lot of it is going to go through, or as much as possible, 100%. But right here on the side is going to be 0%. And then there's going to be all the different percentages in between. So as a whole, how much is going to go through this membrane? Now, mind, the area of this bottom is pi. It's going to be more difficult to get, and the area on the top is 2 pi, by the way. We have done this before. It's going to be more difficult to know what goes through in terms of percentages, because the areas that we're going through are not as unit areas as before. So take that into account as we do this. Anyway, let's figure this out. We need to parameterize, well, let's see, double integral 0, 0, 1 over r crossed with, r sub u crossed with r sub v without taking the magnitude of that. Okay, so let me look at the parameterization, and I guess there's a couple different ways to parameterize. Boy, there's a couple. actually a couple different ways to parameterize. I don't want to repeat necessarily work we've done earlier, but I might do it. So the question is, what are we going to put here for the other vector, which is going to be r sub u cross r sub v, with respect to some area over some d. Okay, guys, that depends on what you use for parameterization. So let's use method 1. So what goes here depends on the parameterization. Let's use a trivial parameterization, trivially. Okay, so r of xy could be xy z. Let's just put z, where z, by the way, is going to be the square root of 1 minus x squared minus y squared. There we go. So that's a trivial parameterization. R sub x is going to be 1 o z sub x. R sub y is going to be 0 1 z sub y. R sub x cross R sub y will be negative z sub x, negative z sub y, and 1. Interesting. So the double integral over the surface. What is the surface? We're just going to call it S. The vector field is going to be 0, 0, 1. R sub x, R sub y will be negative z sub x, comma, negative z sub y, comma, 1. Oh, since we're using this parameterization, which is the trivial parameterization, the surface is not S anymore. It would be D, which is the circle, the unit circle on the floor. So that would be unit circle on the floor with respect to the area. Huh. Well, the dot product of those two is just going to give us 1. Boy, that's interesting. So we're integrating area over the unit circle. Well, the area of the unit circle is 1. And we know we're doing the area because we're just integrating 1. And the reason why it is 1 is because we got the dot product of this with that. So that the answer is pi. The second method of doing example 11 would be to parameterize. So example 11, method 2, we got the semisphere. And remember how we parameterize the semisphere. Let's see, R of uv would be cosine u, sine u, cosine v, comma, sine u, sine v. Whoa. So we need to do R sub u. I think we've done this before. Let me double check. That was earlier, or in a previous video, we did this. No, I don't think we've done it in this video. No, not in this video. We did it in a previous video. It's going to be sine of v. Let's do it real quick. Okay, so negative sine u, cosine u, cosine v, cosine u sine v. My cross product is going to be awkward. 0 negative sine u sine v and then sine u cosine v. So the cross product is going to be those two, r sub u cross r sub v. Wait a minute, I could work really, really hard and get the 3, but what do we want after all? We want the double integral of f with respect to s over the surface, but that is the double integral of 0, 0, 1 multiplied with dot multiplied with r sub u cross r sub v with respect to the area. We're going to talk about the area in a moment, which area we're talking about. But all I care about is because of this vector and the dot product, we care about only the third coordinate, because we're going to end up multiplying 0 times whatever the first, whatever it is here, blah, 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 times 0 when we do this dot product. So we don't really care what that is. Same thing with the second. So we can just do blah, 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 comma, we can yada, yada that part. And what we really care is the third coordinate. And that's going to be negative, and negative is positive. Sine squared u sine of v. Okay, so let me bring this down here. So that is going to be the double integral of sine squared u sine v. And remember, under this parameterization, u and v go from 0 to pi in both cases. So sine squared of u from 0 to pi with respect to u, this is a constant with respect to u, so we can factor that out. So I'm going to do those. Let's split it up. We really have from 0 to pi sine squared of u du multiplied with the integral from 0 to pi sine of v dv. This, I'll let you do that, but remember, this is 1 minus cosine of 2 theta. So there's the 1/2 because the cosine is going to end up being 0 because of that. So we're going to end up with pi over 2. Here, we're going to have negative cosine, but we start at pi, so that is -1 times the negative of the negative cosine. That's 1, but then we're going to subtract 1, so we're going to have 2. And the answer is going to be pi, which is consistent with the answer we got in the first method. So just be aware there is as many ways to obtain the answer as ways in which we can parameterize the surface. Yep. Let me just double check something very quickly here. Yeah, integrating with this vector field made things quite easy because we did not have to figure those out. Just bear in mind that those would have been, since z is equal to square root of 1 minus x squared minus y squared, this would be negative, let's see, there is a negative 2x, so negative of negative 2x over this, well, 2 times the square root of 1 minus x squared minus y squared. So the 2 simplify, so we end up with x over the square root of 1 minus x squared minus y squared. So if those two were not 0, we would have to find those and then multiply and then add with the dot product. And just one of them would have been this guy, which is already rather complicated. So just negative z sub x would have been complicated here. So things can get very, very complicated very quickly depending on the parameterization. That is not to say that this parameterization is any better. Remember, we didn't find here those two components again, but they would have been quite extensive. You know, we got to do the cross product, and there's a lot of things. So again, we did not use that because of this vector field. Had this been, I don't know, x, or not to mention if you had x, y, or z, boy, then there's more to do. Yeah, then you would have to use this as x, this as y, and this as z, depending on what it calls for, the vector field calls for. So the bottom line is this is not easy, not easy at all. It's very complicated. Each problem, sometimes when I'm tired, I get the wrong answer a couple times. Yeah, it can take me 1 hour, 2 hours to do one problem, because especially when I'm tired, because I have to go back and check and double check, and then I keep missing little mistakes here or there. These problems are very, very involved, and that's the nature of them. That's the way they are. Yep. All right, with this, we will stop this video about surface integrals.